Hey everyone, so I could tell at least a few of you were still a bit confused about the quantum numbers after class today, so I wanted to take a minute to make a supplemental video to walk you through what we talked about in those last 10 minutes of class. So in class we established that the parameters for the quantum numbers, and there are four of them, n, l, m sub l, and m sub s, are solutions or come from solutions to the Schrodinger equation. So the Schrodinger equation represents the wave function, or where the electron would be as a function of position in space. If we take the square of that wave function, then it gives us the electron density as a function of position in space. So when we take that square, it can tell us where we would be likely to find an atom or an electron inside of an atom. And it's from the Schrodinger equation that we can pull out the rules that dictate the values that are allowed for L, ML, and M sub S for a particular value of n for a particular atom. So the first or principal quantum number, the n, is another name for our n is our shell, is relatively straightforward because n is literally the same definition of n that we've been thinking about even when we were talking about the Bohr model of the atom, or the hydrogen atom, and that n corresponds, n is, we could think of as the energy level, or which corresponds with a row or period of the periodic table. And so as we increase in n, we get further and further away from the nucleus of the atom. And so as we increase in n, we increase generally the number of orbitals. We increase the number of orbitals that are accessible to electrons. And as we increase in n, we increase in complexity and the types of orbitals where electrons can hang out. So after we've established our n, then we can which is our shell, the angular quantum number, or the next quantum number, or quantum number 2, L, tells us the subshell. And so these are where the subshell basically is our type of orbital. And so our type of orbital is told, is given to us by the L, and the different types of orbitals come from different solutions for the L. So, and the L, related to the N, the values that can occur for a particular value of L are 0 to N minus 1. So if we are at N level 1, N1 minus 1 is 0, so the only subshell that we can have in level 1 is a 0, which we know is an S. And so it's that nice round circle shape. Now, once we go to quantum level, or energy level 2, or shell number 2, we have more options. So we start with 0, so we're still going to have an S, and we're going to have an S in every single N. But we also have the option of 2 minus 1, which equals 1. And so an angular quantum number, or subshell number of 1, corresponds to our p orbital, which has that nice infinity shape to it. Now, after we get to our angular quantum number, we have our magnetic quantum number. And so the magnetic quantum number tells us the number of orbitals in our subshell. And the numerical relationship that determines the number of orbitals is that we go from minus L to plus L through 0. So if we were to look again back at n equals 1, our n, we have an L value of 0. So negative 0, positive 0, no such thing. We just have 0. And so that means we are only going to have one orbital in our S subshell or L equals 0 subshell. Again, things get a little more interesting or complicated when we get to our P subshell or L equals 1. So when we have L equals 1, this is our P orbital or our orbital that looks like this. Our values of ML can go from negative L through 0 to positive L. So if our value is 1, if our L is equal to 1, then our ML can equal negative 1. It can also equal positive 1, and then we go through 0 to get between the two. So we can have a total of 3 p orbitals. And that makes sense because, as we'll talk about on Friday, we can have p orbitals that are oriented in different directions. Now, our negative 1 corresponds to 1 p orbital. Our 0 value for ML corresponds to another p orbital. And then our third value, or positive 1, would stand for our third value. Now, where the fourth quantum number comes in is that within those individual p orbitals, there can be 2 electrons, but those electrons have to be in opposite spins. So our N tells us where, like relatively, what energy shell the electron is in. The L tells us what shape is the orbital, so is it an S, P, D, or F orbital? The magnetic quantum number, tells us which specific orbital within that shape the electrons are in. And then finally, the fourth quantum number, or the spin quantum number, allows us to narrow down which particular electron within that orbital it is. Is it the electron that's spin up? Is the electron spin down? Is it the person on the right side of the bed, or is it on the person on the left side of the bed? So we can also to carry this further to D and F orbitals. So for D, D is our quantum number of, or angular quantum number of 2. And so our allowed values for M sub L for D are -2, -1, 0, 1, and +2, which means we have 5 total orbitals. For F is our L equals 3. So we can have -3 to -2, -1, 0, 1, 2, and 3. So the reason why we stopped at n equals 4 is not because we stop having shells at n equals 4. We actually stop at, we could carry it out to n equals 7, at least with our current knowledge of the periodic table. However, there are orbitals that are added at each energy level. And so I mainly want you to focus through P and D. But knowing what we know about quantum numbers, we could also predict how many orbitals there would be for higher level orbitals. So let's say we have an L equals 4. This would be a G orbital. So why don't you take a minute, pause, and predict how many individual orbitals would be contained within a G-shaped orbital. So the M sub L values for L equals 4, that goes from -L to +L through 0. And so you go from -4, -3, -2, -1, 0, 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So for a G orbital, so for the G-shaped orbital, we would have 9, or the D subshell, we would have 9 individual orbitals. Okay. All right. So then the next application of this, and you'll be answering a question about this on the pre-assignment for Friday, is using those rules. How do we know which quantum numbers are valid? And so if we have an n equals 1, that means we're at shell 1. And if we're at shell 1, our L can only equal n minus 0 to n minus 1, which means we can only have a value of 0. So for shell 1 with L equals 0, that means our ML has to go from minus L to positive L. And again, we only have a value of 0 for our L, so the only allowed value of ML we can have is 0. And in this case, we have an ML of minus 1, so A is not a valid option. In the pre-assignment, what you'll do is you'll look at B through D and decide whether or not they're valid. All right. Now, another type of exercise that you may be asked to do is to be given a particular set of quantum numbers. How many possible solutions will that electron have? And so I'm going to take the example of, let's say we have an electron with an n equals 3 and an L equals 1. So level 3 and then p orbitals. So let's start here. So let's say we have our n, we have our L, we have our M sub L, and our M sub S. So we're stuck with our values that have a value of 3 for the N and 1 for the L. So if we remember M sub L, our M sub L is equal to minus L to plus L. So for M sub L, we can have values of minus 1, 0, and positive 1. And then for our M sub S, we can have values of plus or minus 1/2. So what we'll do is we'll go through for all the different possibilities that meet the criteria for having an n equals 1, and an 3, and an L equals 1. So we have 3 different values for M sub L that are valid, and then for each of those 3 values, we can either have a spin of plus or minus 1/2. So let's start walking through this right now. So let's start, we have an M sub L of minus 1, and then our spin for that can be plus 1/2, but we can also have the same N, the same L, be in the same orbital, and then have a spin of an opposite orientation. Similarly, if we have an M sub L of 0, so that's our second p orbital, we can have 2 electrons in there, one with a spin of positive 1/2, and then another with a speed of minus 1/2, spin of minus 1/2. And then we have one more allowed value for M sub L here, and that's plus 1. And so for our plus 1, again, we can have 2 electrons in that individual orbital with either a spin of plus 1/2 or minus 1/2. And so these are all of our different possibilities. We have our 3 different possibilities for M sub L, and each of those possibilities for M sub L can have 2 electrons. So that gives a possible total of 1, 2, 3, 4, 5, 6. 6 solutions for an electron that has the principal quantum number of 3 and an angular quantum number of 1. Now, in theory, you could also go and remove the parameters of L and then walk through how many solutions you would have for n equals 3, L equals 1, and L equals, and then ML is not set and MS is not set. And so in this case, for n equals 3, our allowed values for L are from 0 to n minus 1. So we can have 0, plus 1, and then plus 2. And so what you'll have to do for n equals 3 is you'll have to include all the different possibilities for M sub L and M sub S for each value of L. And so that's going to be one of the questions on the pre-quiz, and I will post a solution to these questions from the in-class notes on the internet. If you have any questions, as always, feel free to ask.